Okay, so hello everyone, and I am Aniruddha from IIT Indore. We are meeting for the 8th week discussion on the course of measure theory by NPTEL, and let us just recall what all things we have done. And I know we have done in the sense what all things we have done in the lectures. And today we are going to look at a few examples, at least as much as examples as time permits, of measurable functions. Most of them are easy functions to look at, but what we want to do is we want to approximate them using simple functions as done in the theory. So theoretically, we know how to do it. We would like to see how that actually looks. And the second thing we want to do is we want to use that approximation of simple functions to get the integral of the measurable functions that we will define. So most of the functions, in fact, all of the functions that we will define will be on R, because I feel that that is the most easiest space to look at. And towards the end, if time permits, we will also look at a few examples where we will see a strict inequality in the Fatou's lemma and one application of monotone convergence theorem, although it is non-trivial, but it is not very difficult as well. So we will see. So, okay, let me just recall what all things we have done. So, we have seen measurable functions. We have seen integration of simple measurable functions and non-negative measurable functions. And then we proceeded to integration of any measurable function. Simple measurable functions, non-negative measurable functions, and then any measurable function. Or perhaps I should say extended real valued measurable functions. And that particular notion of integration that came from that approximation of measurable functions using simple functions. And that notion later on gives us something called as the monotone convergence theorem. The monotone convergence theorem says that if we have a increasing sequence, or rather a non-decreasing sequence of measurable functions which converge pointwise to another measurable function, and if everything here is non-negative, then we can say that the individual integrals of those sequence of measurable functions, that sequence converges to the integral of f. So fn non-decreasing, fn converges to f, non-negative as well. Then we have seen that f is measurable, and integral f d mu is limit integral f and d mu. This is what the monotone convergence theorem says. The next thing we saw was the Fatou's lemma. What it says was if we have any sequence, it may not converge anywhere to any function, or it may not be even decreasing, increasing, non-decreasing, or it may not have any properties which we desire, but still we can construct another sequence out of it, namely the the lim-in phase sequence, and then we can have a similar estimate. So it says that given a sequence of measurable functions, non-negative measurable functions, we have integration of lim-in fn d lambda. This is less than or equal to lim-in a integral fn d lambda. And later on we saw dominated convergence theorem. What it says that suppose we have a sequence of, again, any measurable functions, and their absolute value is bounded by an L1 function. So not only is G measurable, but its integral is finite. Then if Fn converges to F pointwise, we have that f is in L1, and integral of f d lambda or d mu, this can be given by limit integral f and d mu. So all these results are important in the sense that each of them tells us how to interchange limits and integration. In general, this may not be true. There were some examples that were done in the lectures, and one can also construct very simple examples. For example, that one can construct a sequence of functions that converge to zero pointwise, but their integrals are always one. For example, there is this rectangle, the shifting rectangles, namely this. So first rectangle is from 0 to 1, the next rectangle is from 1 to 2, and then so on. So in particular, Fn is chi of n comma n plus 1 or n minus 1 comma n, whatever. Then Fn converges to 0 pointwise, but limit integral Fn, this is 1 which is not 0, but the 0 is limit integral f. Here x is of course r. So all these interchange of limits and integrations, they are not in general true, but there are certain conditions in which we can do the interchange directly, or at least we can have some estimate. Okay. So today we'll be looking at examples as I promised. Before we begin, if any online audience or anybody has any question, they can ask me. I'll give you 1 minute time. Okay, so if there are no questions, perhaps we can move forward. Let us look at a few examples. So the first example which I would like to discuss here is this. Let us look at this function from R to R, defined by f at any x. It is the characteristic function of the rational numbers at that point x. That means it is 1 if x is a rational, it is 0 when x is not a rational. So, okay. Now the question is whether this is measurable, and if it is measurable, what is its integral? Clearly f is non-negative, and in fact f is a simple function. Because it is just the characteristic function of rational numbers, it is a simple function. And therefore integral of f d lambda, this is integral of chi q d lambda over r, which is the measure of q. But what is the measure of q? Since q is countable, it must be 0. So this was one of the sort of a trivial example where we get a non-negative measurable function, and we can evaluate its integral directly. So notice that we don't need to approximate this function using any simple function, because it itself is a simple function. So let us look at another example where we will need to approximate it. So consider f from R to R given by fx is equal to 1 over x when x is strictly positive and 0 when x is non-positive. So how does this function look like? There are no values below the x-axis. So let us not draw that. This function is clearly for positive real numbers, it goes like this. But for negative real numbers, or rather non-positive real numbers, it remains here. The value is 0. And including 0 as well. At 0 also the value is 0. Now we want to know what is the, whether this is measurable or not first. But then it is measurable because it is continuous, and therefore the pre-image of open sets is open, at least for these positive real numbers. Similarly for the non-positive real numbers, and if any open set contains 0, even then one can easily check that the pre-image, it is not open, but it is a Borel set. So F is Borel measurable, or in our sense it is measurable because the pre-image of Borel sets is Borel, so it is, in particular, it is Lebesgue measurable as well. Now let us try to approximate it using the simple function technique that we have. So the technique that we studied during class was, we can approximate f using these type of functions: k from 1 to n 2 to the power n, k minus 1 by 2 to the power n, chi of the pre-image of k minus 1 by 2 to the power n to k by 2 to the power n, plus n times chi of n to infinity. So if we recall, what we used to do was, we divided this codomain 0 to infinity in, say, smaller intervals, and we looked at the pre-image of those intervals, and on that pre-image we kept the lowest value. So if we are to do it here, let us try to write S1, S2 at least. Further, as we move ahead on n, then it is going to cause a big, the expression is going to be too big to write. So let us at least write S1 and S2. That will make things clear. So S1, by definition, it is k from 1 to 2, k minus 1 by 2, chi f inverse, the pre-image of k minus 1 by 2 to k by 2, plus chi of 1 to infinity. So what we have done, let us divide this 0 to infinity into, say, 0 to 1 open and 1 to plus infinity. And even this 0 to 1, I am further going to divide it 0 to half and half to 1. Now on this, whatever the pre-image of this, let us mark it somewhere. So if we notice that the y coordinate is half, so what should be the x coordinate? It should be 2, because the function is 1 by x here. So on this 0 to 2, what we are going to do, we are going to fix the lowest value, that is 0. Yeah. Oh, I'm sorry. That is not correct, because, well, the pre-image of this set is actually everything after 2. This is f inverse of 0 to half. Why? Because, this is collection of all those real numbers such that fx is between 0 and half, but fx is either 0 or it is, if it is positive, then x has to be positive, which means x must be in 2 to infinity. Or of course the negative part is there, but there it is anyway 0, so we are not really worried about it. The only thing we are worried about approximating is this positive part, the positive part of the real line. So here we are going to keep it 0. Now let us look at the other interval from half to 1. So again, let us mark it. See here, notice that here the y coordinate is 1, so the x coordinate must also be 1, because again the function is 1 by x. Now the pre-image of half to 1 is everything between 1 and 2. This is the pre-image of half to 1. closed half, open one. So here what we are going to do, we are going to fix the lower value. So this value. And then again, from 1 to infinity, that is now the pre-image is this. F inverse of 1 to infinity is this. And here we are going to again fix the lower value, that is 1. So this red lines, they are S1. So now from the diagram also we can write it, or directly we can write it here. At k equal to 1 it is 0, and in fact this is also 0 as we can see. The only thing that remains is half. So half, where is it half? From 1 to 2, chi of 1 to 2 plus 1 to, I think, sorry, open 1 to close 2. Because here 1 is open, so this one will be open, but 2 is half is included, so 2 will be included, plus 1 times chi of 0 to 1. Notice that here infinity is included, so 0 is also included. Or perhaps not. I'm really sorry. It is not included. It is open 0. Because at 0 the function is 0. That is how we defined it. Okay, so this was our S1. What about S2? Let us try to write it. So it will be from 1 to, now n is 2, so it is 8. So as you can see, even at the second stage, we have divided the interval too much. From just 2 divisions, we have gone to 8 divisions. K minus 1 by 4, chi F inverse. So just a second. Yeah, now it is correct. K minus 1 by 2 to the power n to k by 2 to the power n plus n times chi n2 plus infinity. So again, let us draw a figure and let us try to approximate it. But this time we'll need a bigger figure. This is our 1 by x. And why am I writing n? This should be 2. Because we have fixed n equal to 2. So again, let us mark this point 2 here. So this onwards, we are not really concerned because we have to just look at the pre-image of this big interval, 2 to infinity. What we are concerned about is the smaller intervals. So from 0 to say 1 will be somewhere here. So 0 to 1 open, 1 to 2 open, and further divide them into 4 equal parts. So 1 by 4, half, and 3 by 4. Every time the left end point is included, the right end point is not included. Similarly, here it would be 5 by 4. Next one would be 3 by 2 and 7 by 4. Always do this, left open, right close, left closed, right open. And now we want to look at the pre-image. So what is the pre-image of this? This is 1 by 4, so it should be 4 comma 1 by 4. So everything after 4, this is the pre-image of 0 to 1 by 4. And of course the negative side, but we are not concerned about it again. From 1 by 4 to half. So what is this point? This point is, well, this is half, so this must be 2. So 2. So from 2 to 4, we have the pre-image of 1 by 4 to half. From half to 3 by 4, this point would be 4 by 3 to 3 by 4. So this is 4 by 3. This one is the pre-image of, well, half to 3 by 4. And then so on. So one can find out what are the points. This is 1 and this would be 4 by 5. And as you can see, these intervals really get smaller and smaller as I come closer to 0. This is 4 by 5, this is 2 by 3, and this one would be 7 by 3. But the last one would be 2, so somewhere half. Of course, this is not drawn to scale, which is why like the half is being drawn really close to 0, but yeah, one can understand. So after 4, this must be 0. In between 2 to 4, the lowest value. In between 4 by 3 to 2, the lowest value. And then this continues. So all these red lines again, they are S2. Now if I want to write it arithmetically, what is this? S2 is 0 times this, and then 1 by 4 times chi of 2 to 4, open to closed 4, plus say half of chi of 4 by 3 to 2, plus 3 by 4 chi of 1 to 4 by 3, plus chi of what will it be, 4 by 5 to 1, plus 5 by 4 chi of the next one is 2 by 3 to 4 by 5, plus 3 by 2 chi of 4 by 7 to 2 by 3, and then there is just one other thing, 7 by 3 chi of half to 3 half to 4 by 7, and the last one, that is 2 times chi of 0 to half. And then we can continue doing this. This is our S2. One can similarly find S3, but it will still be a longer expression. So we are not going to do it here. But yeah, for visualization, one can try to make these rectangles again. Now what we want to do, we want to, at every stage, we want to look at the integral of Sns. So in general, Sn is given by k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, chi of f inverse of k minus 1 by 2 to the power n to k by 2 to the power n, plus n times chi of f inverse of n to infinity, which is, since I know f, this is 1 to n into 2 to the power n, k minus 1 by 2 to the power n, chi of 2 to the power n by k to 2 to the power n by k minus 1. Because see, if f is 0 somewhere, then it won't matter because the lowest value is still 0. So whatever the interval, that integration is going to be 0. On the other side, if f is non-zero, then it must be positive, in which case fx is 1 by x. So f inverse is also 1 by x, and we can just invert the interval to get the pre-image. Plus n times chi of 0 to 1 by n. And notice that infinity is not the image of anything. So this pre-image of this interval is same as pre-image of closed n, open infinity. Okay. Now let us, all we have to do is compute this integral, which is easier because we know by definition this is equal to k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, and the length of these intervals, 2 to the power n by k, 2 to the power n by k minus 1, plus n times the length of this interval, 0 to 1 by n. And we know how to calculate lengths of intervals. Just look at the endpoints and subtract the smaller one from the bigger one. So it is k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n into 2 to the power n by k minus 1 minus 2 to the power n by k plus n into 1 by n. So this is 1. It doesn't really matter. It doesn't depend on n at all. K equal to 1 into n 2 to the power n. K minus 1 by 2 to the power n. So this 2 to the power n can go away. So from here I can just cancel this off. And this is k minus 1. So it is 1 over k into k minus 1. So this k minus 1 can also go away. What remains is 1 over k plus 1. But this series does not converge. As a consequence, limits of essence do not converge. And since they are all non-negative, this is an increasing sequence. This must be plus infinity. And by definition, integral of f d lambda over r, this is limit n going to infinity integral Sn d lambda over r, which is plus infinity. That means we have an example of a measurable function which is not integrable. F is not in L1V, or in this case L1 lambda. Okay. So if we look very closely, the problem is that near zero we get this type of a series, because as we increase our n, what we are doing is near zero we are making smaller and smaller rectangles. But every time I make this smaller rectangle, 1 by k appears somewhere, and I keep on adding this, I am going to get plus infinity. So one might ask, what happens if we remove some part after 0 and consider this 1 by x after that part? That means, let us look at this function. So consider f from R to R as follows. Yeah, although evaluating it may be difficult, but I'll give you an idea and one can try. So fx is 1 over x into chi of, see, some delta to infinity for some delta positive. That means, or maybe for simplicity, let us write it as 1 to infinity. So 0, 1, somewhere here 1. So the function is only this part of 1 by x. Everywhere else it is 0. So now if I approximate using simple functions, notice that this is a bounded function. So again, by definition, it is n into 2 to the power n. What was it? K minus 1 by 2 to the power n. Chi of the pre-image of k minus 1 by 2 to the power n to k by 2 to the power n plus n times chi of n to infinity. Now, whatever n I take, this chi of n to infinity, pre-image of n to infinity is either going to be a singleton set in the case when n is equal to 1, or otherwise it is going to be empty. F inverse n to plus infinity. This has only two possibilities. This is singleton 1 if n is 1, and it is empty if n is bigger than or equal to 2. So there is no contribution whatsoever from this part. No contribution to the integral, of course. The only contribution that comes is from the other part. Okay. So let us see what issue will happen here. Again, the same problem. So here, these smaller rectangles were causing a problem. But then later on, as we see, even here we get these smaller rectangles, right? Now they are going to cause a problem, because if you look closely, this Sn now becomes k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, chi of this same thing, 2 to the power n by k to 2 to the power n by k minus 1 for n bigger than or equal to 2. And then we have seen that if we have such a thing, I can write it as k from 1 to n into 2 to the power n, 1 by k, which is still not convergent. So even this f, it is not a integrable function. Okay. So usually what we say is that, yeah, and one can also check what happens if we remove the other part. So for example, if we consider this function, fx is equal to 1 over x chi of open 0 closed 1. That means we have something like this. So at 1 and then this. Everywhere else it is 0. In this case, what is Snx? K from 1 to n into 2 to the power n. K minus 1 by 2 to the power n. Chi of the pre-image of these sets. K by 2 to the power n plus n times chi of the pre-image of n2 plus infinity. Right. So now let us look at what these pre-images are. As before, we cannot say that f inverse of n2 plus infinity is empty, because actually this is unbounded near 0. So, these will always contribute. In the integral. What does not contribute is f inverse of k minus 1 by 2 to the power n to k by 2 to the power n. This could be empty if k by 2 to the power n is less than or equal to 1, which is same as saying k is less than or equal to 2 to the power n. And therefore, this Snx actually, or maybe since I'm not writing x on the right hand side, let me not write it on the left hand side as well. So Sn is actually k from 2 to the power n. Yeah, at 1 it is non-empty, because at 1 there is the singleton 1. So it is strictly less than 2 to the power n. So 2 to the power n to n into 2 to the power n, k minus 1 by 2 to the power n, chi of f inverse. So I can now write what is f inverse. F inverse is 2 to the power n by k to 2 to the power n by k minus 1 plus n times chi of 0 to 1 by n. So this was as before. There is no change at all. But what happens is at k equal to 2 to the power n, this is, this is from 1 to something, and that is just singleton set, right? I should have written plus 1. And there is another term for 2 to the power n. Hello, Robin.
Hi, Aniruddha. How are you?
I'm fine. So
I'm
I
so
was just
sorry.
discussing.
So sorry. I was supposed to come in last week, but because I'm in Sydney, it's kind of difficult. Difference
Yeah,
kind of.
you mailed me last time. I read that mail.
But thank you
It
so
is
much.
all right. So yeah, actually, what we were doing is we were looking at some examples of measurable functions, and we were trying to approximate them using simple functions and
Yes,
see
yes.
whether they are integrable or not. So this example I was looking at, what happens if I look at 1 by x.
Mm-hmm.
So after certain computation, let me just quickly go through it. So this Sn, the approximation by simple functions, it turns out to be like this: k minus 1 by 2 to the power n, chi of
Yes.
2 to the power n by k, and so on. And it turns out that this integration is, the sequence of integrals does not converge, because we get the harmonic series 1 by k. And therefore, this f is not in L1. In particular, 1 by x is not in L1. This is not an integrable function. Then, the problem which it seems is that since it is unbounded both the sides, we are getting infinitely many rectangles,
Mm-hmm.
and that is causing a problem. So next thing what I did, let us just truncate it towards left, so that now it is a bounded function. Let
Mm-hmm.
us see what happens. Even in this case, if we look at Sn turns out to be, I mean to say integral Sn. Integral Sn again turns out to be this harmonic series, which is still divergent. So even after truncating it, it is not a L1 function. So now I was just looking out of mathematical curiosity, what happens if I truncate it towards the right?
Yeah.
Okay. So, okay. So we have this Sn as sum of k minus 1 by 2 to the power n, chi of 2 to the power n by k to 2 to the power n by k minus 1 plus n times chi of 0 to 1 by n. And there is one term of the singleton set when k is exactly equal to 2 to the power n, that is 2 to the power n minus 1 by this into chi of singleton 1. Now if I integrate it, this is equal to sum from 2 to the power n plus 1 to n into 2 to the power n, k minus 1 by 2 to the power n, and then this is again, it is going to be 2 to the power n by k minus 1 minus 2 to the power n by k plus 1 plus 0, because the measure of singleton sets is 0.
Yes.
And again, this turns out to be the exactly same thing. So this is 1 over k. And it is still divergent.
Because it's the harmonic function, right?
Yeah. Yes, it is still the harmonic series. It is still divergent as n goes to infinity. So no matter how we truncate this 1 by x towards the right or towards 0, this is not an L1 function.
I had a question about the L1 functions. So from the notes, what I have conjured is L1 is basically the space of all mu integrable functions, right? If I'm not wrong.
Yes, yes.
So
yes, they are all.
So the problem that I'm having is, how do I identify whether, like, if I know you've shown an example, but if I were given a function, right, how do I identify whether it's an L1 function or not? Like, what are the properties? Do I have to go through the 4 properties that the professor showed out, or do I just have to show that, okay, the function f is actually mu integrable, which basically means that it follows that the function f is measurable. So just check whether the function is measurable or not.
No, that is not enough, right? This example precisely shows that, because 1 by x is measurable, but it is not not lambda integrable.
Lambda is
the length. I mean the Lebesgue measure.
Can you just show me what Lebesgue measure was again? Because I completely forgot. I forgot the properties to show what how to derive whether how to identify whether a function is Lebesgue measurable or not.
Oh, Lebesgue measurable just means that given a function from R to R, look at the Borel sets here. So this is a Borel set. Then F inverse of this Borel set should be inside the Lebesgue sigma algebra of R. This is the definition of measurability of functions for us. Or we usually call it as Lebesgue measurable.
Can you give an example? I know I did it, but I'm just trying to figure out.
Okay, so perhaps we'll look at some non-trivial example, right?
Yes.
So let us consider, say, well, what do you want to consider? Suppose let us consider sin x.
Yeah.
Okay. Now, is sin x a continuous function?
It is. It's continuous.
It is, right?
It is continuous.
So f is continuous implies that if I take an open set in R, the pre-image is going to be open.
Yes.
Right. Okay. So if what I am saying is that every the pre-image of every open set is Lebesgue measurable, right? Therefore, yes. F inverse E is in LR. But then we have seen that these type of sets, such that E comes from this Borel sigma algebra, this itself is a sigma algebra, right?
Okay. Yes. Yes.
Actually, no. This may not be a sigma algebra. I meant to write the other way. So I
The
meant to say, let us look at all those Borel sets such that F inverse E is inside LR.
yes. So the set of so yeah the Borel sets make up the sigma algebra.
Correct.
Yeah.
So this itself is a sigma algebra,
Yeah.
and this contains the set of all open sets. So this must be equal to all of BR, right?
Yes.
So therefore, this, by our definition of Lebesgue measurability, in fact, we have proved that every continuous function is Lebesgue measurable.
Yes, that was one of the conditions. Yes.
Right. So in general, if you like at this stage, because we have not looked at a lot of properties, at this stage you have to check using this definition.
So basically, what would I? So check whether the function is continuous or not. If it is continuous, check whether the pre-image is in R.
No.
R
The
is
pre-image is open. Yeah.
oh
To
yeah.
check whether a function is continuous, you have to check that the pre-image of every open set should be open.
Yes. And then if it's open, then that means that it's in the Lebesgue. Then the function is Lebesgue measurable. And
Right.
if it is Lebesgue measurable, then it means that by default it is also it's in the Borel set as well.
No. It is the other way around. The Borel sigma algebra is contained in the Lebesgue sigma algebra.
The Borel sigma algebra is in the. So so how do I? So Borel does not necessarily mean that it's Lebesgue, right?
Borel set or Borel measurable?
Yeah, if it's Borel measurable, then it is Lebesgue measurable as well.
No. If actually there are two things which might cause a confusion. Do you want to ask that Borel sets are Lebesgue sets?
Yes.
Yes, this is true. But Borel measurable functions need not be Lebesgue measurable.
Can you explain why?
Because what do we mean by Borel measurable functions? Borel measurable function means that F inverse E, F inverse E, sorry. I mean to say the other way around. Yeah, Borel measurable functions are Lebesgue measurable because anyway Borel sets are Lebesgue sets, right?
Yes.
Yeah.
So Borel measurable functions are also Lebesgue measurable.
Correct. Yes. But the other way around, it may not happen. Lebesgue measurable functions need not be Borel measurable.
Lebesgue measurable functions need not be Borel measurable, but Borel measurable functions are always Lebesgue measurable.
Are always Lebesgue measurable. Yes. In fact, this proof actually uses that fact, right? What we have proved is actually F is Borel measurable because the pre-images are all open and therefore in the Borel sigma algebra.
Yeah.
But then that is in turn contained in the Lebesgue sigma algebra, therefore it is Lebesgue measurable.
Thank you so much for that. I kind of got that confused, but like it was a little confusing.
Happens sometimes.
I remember I wanted to ask 3 questions from the assignment that I got wrong, which is question number 1.
From the previous week?
Yes.
I don't have the questions with me right now. Let me just open it. Let me see. Do you have the questions with you?
Yes, I do. So if X, if X, S, and mu, do you want me to share?
You could share the screen. That would be better.
This one.
Okay. So excess mu is a measured space. State whether true or false. The integral f d mu exists for every non-negative measurable function, if and only if x is sigma finite.
Yes.
Actually, there are sigma finite measure spaces in which exist in the sense of plus infinity, right?
Yes.
So why do we require sigma finite there?
I I'll be honest with you. I kind of forgot the definition of sigma finite.
Oh,
I
sigma
tried.
finite.
Sigma finite means that the function the function might not be finite on R, but if you took a sigma algebra over R, so for example, if you took Lebesgue sets or Borel sets, then and you define the function on that sigma algebra, then the function is finite.
No. That is not sigma finite. Sigma finite definition is this. So a measure space. Oh yeah, I forgot to share. Let me quickly share it. Yeah. Okay, so is this screen visible?
Yes, it is.
So sigma finite measure is this, that if excess mu is a measure space, and X can be written as a union of xn's with measure of xn's finite, then this is called a sigma finite measure space.
So if you defined mu on every xn such that xn the disjoint.
Not necessarily disjoint, but yeah. Sometimes it may be an increasing sequence as well. For example, in R, what we can do, this R, the measure of R is not finite, right?
Yeah.
But we can decompose it like this: -1 to 1, -2 to 2, and so on. That means at each stage, I just define it -n to n. And the measure of each of these xn's is finite.
Yes. Non-negative. Wait. I have it. I know I have it. Where is it? Non-negative measurable function is. Let me just. I might have forgotten. But yeah, it should be. I think it is. Non-negative. I have it in my notes, but I don't have it.
Okay, no problem. So it is defined to be the limit of integral Sns, right?
Oh yes. My bad.
Where Sn is an increasing sequence that converges to f of simple functions.
Yes, so, Sn is a sequence of simple functions. Is a sequence of simple functions, and when you take the limit over Sn, that's when you get n. I'm sorry, that's actually in one of the assignments, because we had to. It's actually in one of the questions in the assignment. I'm sorry about that.
No issues. So if we can see this, Sn is an increasing sequence. Therefore, integral of Sn is also an increasing sequence, right?
Yes.
So this limit is always going to exist, whether or not this space is sigma finite.
Why would it exist if?
Yeah, exist. When we say exist, in the sense of extended real numbers.
So it can go up to. It can go up to infinity. Exactly.
Correct. So either it is bounded, in which case the limit exists finitely, or it is plus infinity, right? So it always exists in R star, and whether or not this X is sigma finite, we can always define this integral of a non-negative measurable function.
Oh. I think I took it for the finite sense. I was like, okay, if it's sigma finite, then it might be, then the limit exists and it's finite. My bad. I'm so sorry about that. The other two questions that I had were the last.
Could you share it again on your screen?
So number 9 and number 10.
Okay. So. Yeah. So see what can happen. Let us.
I'll stop sharing. Thank you.
So I actually saw only question number 9, but okay, question 10 we'll discuss later. See, f and g are non-negative measurable functions. That is all it is given, right?
Yes.
It is not given that they are L1 functions, right?
Sorry, pardon?
It is not given that f and g are L1 functions.
L1 means they're mu integrable. I'm still a little confused with L1 and N plus.
See, L plus means that they are just measurable. We are not talking about their integrability.
Yeah.
But when I say that f is in L1 of mu, it means integral of mod
and
f1 is finite.
so their integration is finite. So
Right.
which means
The integration is finite.
so they're measurable and their integration is finite.
Exactly.
Okay.
So by definition, L1 mu is always sitting inside this measurable subsets,
Yes.
measurable functions, right?
Yes.
But the other way around may not be true. For example, let us look at this function from R to R. Let us define it as chi R, that is identically 1. Okay. Now this is a non-negative measurable function because it is a constant.
Mm-hmm.
But integral of f d lambda is plus infinity.
Yes.
Now let us take g equal to f, and what about f minus g then?
Undefined.
No. F minus g is defined, right? F is identically 1, g is identically 1. So what is f minus g?
Sorry,
I'm not saying integrals. I'm saying f minus g. As functions, f minus g, what is it?
Oh, f 0.
0, right? So
Yeah.
integral of f minus g is 0. But integral of f minus integral of g, this is not defined.
This is undefined.
Right? So in general, if we just have measurable functions, integral of f minus g may not be equal to integral of f minus integral of g.
But wasn't there wasn't there one of the properties that the linearity
No,
holds?
we never proved it for negative constants, right? We only
Yeah.
proved that integral f plus g is integral f plus integral g,
Yes.
and integral of af is a times integral f for a non-negative.
Yes.
We never proved what happens when a is negative.
No. And we didn't prove it for a negative function as well. So if g were negative, yeah, we didn't prove it.
We
But
never proved anything for negative functions. So
okay,
actually,
so
this is the exact problem for negative functions, right? One could
yes,
go to plus infinity, the other could go to minus infinity, and then the difference is not. I mean, the sum is not defined.
and now it makes a lot more sense. And the last question, I promise this is going to be the last question, which is it's this one, number 10, which is basically why is it not a precondition that f must be non-negative? Like I can understand why, but I just cannot logically deduce it, like mathematically show it.
Define this. Then mu f is a measure if and only if f is non-negative.
Yes.
See, we have to prove that it is. Could you stop sharing?
Yes.
See, we just have to prove that this mu f is a measure or not, right? How we defined it? We defined it as mu of f inverse e.
Yes.
Right? So, since f is measurable, this f inverse of e always belongs to this S, right? For every e in the Borel sigma algebra. Correct?
Yes.
Now, what has this got to do with f being non-negative? Nothing, right?
So f can be negative.
Yes. For example, let us take f as identically minus 1, the constant function minus 1.
Yeah.
So, is it measurable? From R to R, let us take.
It is measurable, right?
It is measurable, right? So, what about mu f then? Mu f of e is mu of f inverse e, and f inverse e has only two possibilities, right? Either it is empty when this 1 does not belong to e, or minus 1 does not belong to e, or it is all of r, in which in the case when minus 1 belongs to e.
Yeah.
Right? So it takes only two values, 0 and plus infinity. Minus 1 does not belong to e, and when minus 1 belongs to e. So is it now with this definition, is mu f a measure? let us quickly check it. Is mu f of empty set empty? Sorry, is mu of empty set 0?
Yes.
It is 0, right? Because 1 does not belong to the empty set.
Yeah.
What about the countable additivity? So if we have this disjoint union of ENs, again there are two possibilities. Either it is 0 when -1 is not in this union, and it is plus infinity when -1 is inside this union, right?
Yes. Aniruddha, can you explain a step before when you said that mu? I think it's mu r. Is that how it's defined?
No, I'm writing mu f for this f as identically -1.
So mu of empty set equals to -1 if mu of the so mu of f inverse E is equal to mu of the empty set, which is if -1 does not belong to E. The other one is the other option is it is mu of R if -1 does belong to E. Can you explain that?
Yeah, because the function I am considered is this f is identically -1.
Yes.
So what do you mean by f inverse of a set E? It is the collection of all those elements in R such that fx is inside E.
Yes.
But fx is only -1, right? This is the collection of all those elements in R such that 1 is inside E.
So would it be -1?
Sorry, yeah, -1. Such that -1 is inside E.
Yeah.
So this is empty when -1 is not in E, because then there is no element such that -1 is inside E.
Yeah.
Or it is all of R when -1 is inside E, right?
Oh. Yes. Sorry.
Actually, the condition is really independent of X.
Yes.
It is a universal condition. So
because the domain of the function can be anything in R, and I'm so sorry about that.
So there are only two possibilities.
So mu of R is infinity. So okay, so we have defined mu. It is a measure.
Suppose it is a measure, right? In this way, it becomes a measure. But here we have this f. It is not non-negative. It is strictly negative, right?
Yeah.
So using this definition, it does not imply that whenever mu f is a measure, f is non-negative. That's why that statement is wrong.
Okay. So basically, whether a function is negative or non-negative has no bearing on whether it's measurable or not.
No.
Okay.
We can have negative measurable functions, right? For example, the negative constants.
Yeah. So let me just write that down. Whether Aniruddha, are you going to be uploading these notes?
Yes. I usually upload it immediately.
Thank you so much. Whether the function is non-negative has no bearing on its measurable. Thank you so much. Aniruddha, the other question that I had was, I actually got Professor's book, and I was going to ask, which chapters do I need to focus on?
I have no idea right now. Perhaps I can tell you later.
If you can let me know, because that would be great. I have this.
Yes.
So,
you can look at the contents and you can compare it with this NPTEL syllabus.
Yeah, but it's a he starts off with he has Riemann integration, which is
the motivation for defining this Lebesgue measure and all. It starts from the Riemann integral.
So do you think that I should revise that?
I think we are going to cover it in the next week, the connection between Riemann integration and the Lebesgue integration. So I think you should start reading that.
Okay, so there's Riemann integration, which is chapter 1. Chapter 2 is extending Riemann integral. He defines Lebesgue recipe in, I think, 2.2. General extension theory, I think that's where he talks about
that. The sigma algebra comes from there.
Yeah. So, and then the Lebesgue measure on R and its properties. I think that's the chapter that I really need to focus on.
Yes.
Chapter 4 and chapter 4 and chapter 5, which is integration. This chapter 7 has measure and integration on product spaces. Do I need to?
Yeah, that would be the topics of the last week or perhaps last 2 weeks. So, but it is good to study it because later on it really helps. So, are you from a mathematics background or
No, I'm
which
actually
background?
from a statistics and computer science background, so it's a.
Okay. So, I think you will be dealing with probability measures more than.
Yes. That's one of the reasons why I have to do measure theory, because when I go into a PhD in probability or statistics, I have to like. So
Yes,
this
yes, yes.
semester I'm doing real analysis, complex analysis, and measure theory. So they're all sort of helping me to a certain degree. I did probability theory before, which is why a lot of the stuff that I'm doing right now is a lot easier, because especially when it comes to set theory and stuff like that. The only problems that I have is with regards to understanding measurable functions. Like how do we go from measurable functions to simple measurable functions to non-negative and simple measurable functions? All of those, like those transitions, that's where I'm sort of becoming a little confused.
Okay.
Well, I'll,
So,
I'll, I'll probably be fine. Like my marks are okay. It's just that it's sort of connecting all the disjoint. They look disjoint, but they're not disjoint, right? Like every week we kind of think about it as they're all disjoint, but when we take it together, they're all
yes,
interconnected.
yes, yes. They are
Yeah,
all
so
connected.
that's
Yes.
that's the only issue that I'm having. If you another, if it's possible, if you can send through, if you can let me know which chapters I might need to focus on, especially for the exams, that
Yes,
would be
yes.
that I would greatly appreciate it.
Okay. I'll mail you it. Okay.
Thank you so much, Anuradha.
Okay.
I'll
Okay.
probably let you be right now, but thank you so much. Thank
Okay.
you.
Okay. No issues.
Bye.
Okay. So, right. Uh, so well. Yeah. So we were here, and what we saw was that no matter how we truncate this 1 by x, whether we truncate it near zero or truncate it towards plus infinity, this is always going to be a non-integrable function. Similar examples can be constructed for integrable functions and non-integrable functions as well. And perhaps we'll continue that later. Just one example I would like to do here is the following of the application of monotone convergence theorem, since we are out of time. So the example is as follows. We want to evaluate this limit. Integral of n times log of 1 plus fx by n d lambda x. So, or doesn't really matter if it is d lambda x over r, any measure space x. We want to know what this integral is. So, to see this, first notice that this is a non-negative function. This is a sequence of non-negative functions, because log of 1 plus something is positive, n is positive, so it is all positive. Also, log of 1 plus fx by n, n times this is log of 1 plus fx by n whole power n, which is less than or equal to log of 1 plus fx by n, n plus 1 to the power n plus 1, which is n plus 1 times log of 1 plus fx by n plus 1. So why is this true is because log is an increasing function, and this sequence is an increasing sequence. In fact, one can prove that 1 plus fx by n to the power n, this converges to e to the power fx. So therefore, now using this convergence, as I said, n log 1 plus fx by n, this converges to e to the power log of e to the power fx, which is actually just fx. And therefore, by the monotone convergence theorem, one concludes that the limit of these integrals n times log of 1 plus fx by n d mu x over any measure space x. This is equal to integral of fx d mu x. Okay. So, yeah, well, of course, I have assumed that f is a non-negative measurable function. Otherwise, of course, this could be less than 1 and negative. But yeah, we are assuming that it is a non-negative measurable function. So, therefore, or what we can say is that this is finite n into log 1 plus fx over n d mu x. This is finite if and only if f is inside L plus intersection L1 mu. So that means it is a non-negative measurable function as well as it is integrable over that measure space x. Okay. And one last example, another one, to get the strict inequality in the Fatou's lemma. So what the Fatou's lemma says is, if we so Fatou's lemma says that integral of liminf fn, this is less than or equal to liminf integral of fn's. And to see that this it may not be equal, we have this example that let us take fn to be chi of what I have taken n to n plus 1, or one could take other intervals as well, but for the sake of example I am taking this. So how do these intervals look like? So the first one is from 1 to 2, the next one is from 2 to 3, the next one is from 3 to 4, and so on. This is f1, this is f2, this is f3, and the remaining parts, of course, they are 0. So clearly fn converges to 0 since for each x there is some n such that n is bigger than x. This is precisely the Archimedean property of natural numbers. Therefore, x does not belong to this any of these fn's, or rather x does not belong to n plus 1 for every n after a certain stage. And hence fnx is 0 after a certain stage. Now with this in mind that fn converges to 0, since it is convergent, this liminf is same as 0. And hence integral of this liminf d mu over r. Right? This is over r. This is 0, which is strictly less than 1. And 1 is the liminf of these individual integrals. Why is that so? Because each of these is actually equal to 1. And the liminf of a constant sequence is the same constant. So, yeah, so we have seen two more examples. One is as an application of the monotone convergence theorem. And the second example is where we can have an strict inequality in the Fatou's lemma. So next time we will continue. We'll look at few more examples of integrable functions, or non-integrable functions for that matter. We'll see how to approximate them using these simple functions, and we'll try to evaluate its integral. So let us stop for today. Thank you.